Here we go. This is going to be part 2 of the video now, where I'll be taking those algebraic expressions and showing you what I mean by the application of them. So we'll go through pretty much all the shapes again, starting with parallelogram. So like we said, the opposite sides here are congruent. So if one was 2x plus 6 and the other was 4x plus 10, then here you go. 2x plus 6 equals 4x minus 10. All right, you can solve that. That's early middle school algebra. Now, they could be annoying and give you an x squared and a 5x plus 6, which will wind up resulting in a quadratic equation, move everything to one side, get it equal to 0, factor and solve. All right, but generally no. All right. Scenario 2. Here you have two algebraic expressions for two opposite angles, which we just talked about in the last video as being equal, so you would set them equal. Obviously, I'm using very simple expressions here, more so just to show you the application. Here we have adjacent angles. Don't set them equal, all right, because that answer will always be there. Instead, you're going to add them up, 4x plus 5x, and set them equal to 180. All right, adjacent angles in a parallelogram are supplementary. All right, here you have two parts of one diagonal, but since we know the diagonals bisect each other, right? Segment bisector divides a segment into two congruent segments. You know that whole deal. So 2x plus 3 must be equal to, congruent, to 3x minus 1. So you would set them equal, solve, and be done. All right. On to rhombus. Again, defining property of a rhombus, all sides are congruent. All right, so if I have any two sides, adjacent, opposite, or otherwise, you would set these two pieces equal. 6x minus 15 equals 4x minus 5. All right, solve and get an answer there. Okay, over here, since you know the diagonals intersect perpendicularly, so there should be a right angle symbol right there. I didn't want to show it to you, but you would need to know that. All right, then you'd have right triangles. You'd have 4 of them. In fact, you'd have 4 congruent right triangles. All right, that you can prove congruent by a bunch of things. Side, angle, side, depending on what you know. It could be hip, leg. It could be side, side, side. There's a lot of different ways. Anyhow, you would then take, hey, hold on, of a right triangle, these are the two legs. I'd be looking for the hypotenuse, so that would be my C that I'm looking for. So 5 squared plus 12 squared equals C squared. In this case, it worked out perfectly. It doesn't always, though. So you would get a side length of 13. Be mindful, sometimes they ask for the perimeter, so since it's a rhombus, you'd have to just, multiply it by 4. So if the side length was 13 times 4, the perimeter would be 52. Okay, so in this case, I tried to use a little color just to differentiate. If all I did was give you this one angle, this 42, but told you it was a rhombus, that's all you need to figure out every other angle. So it's a rhombus, so they intersect perpendicularly, so 90, 90, 90, 90. All right, and I said since the diagonals bisect the angles, that makes this 42, 42, 42, 42, right? So you got 4 42s. But you remember, hey, I got a triangle right here. So all 1, 2, 3 angles have to add up to 180. So if this I know is 42 and this I know is 90, then 42 plus 90 plus x, if you want to go algebraic, would have to add up to 180. All right. Either way, you solve, you'd figure out that missing angle is 48, which gives you 48, 48, 48, 48. So again, groups of 4, 42, 42, 42, 42, 48, 48, 48, 48, and 90, 90, 90, 90, only but a rhombus. Rectangle scenarios. If you have that diagonal, we talked about Pythagorean theorem applying because you know you got a right angle right here. Okay, because all the angles of a rectangle are right angles, aka diagonal rectangles are equiangular because all the angles are 90. They're all the same. So if I have a 9 and a 12, I can set up Pythagorean theorem and find the diagonal there. 9 squared plus 12 squared equals x squared. Obviously, if I knew the diagonal, I could always solve for a missing leg if that was the case. Okay, in this situation, if I tell you that AC equals 3x plus 15, so 3x plus 15 from there to there, and BD is 6x minus 9. Now, this is only going to work with a rectangle. All right, the rectangles' diagonals are equal, so you would set them equal to each other. 3x plus 15 equals 6x minus 9. All right, keep in mind, with a parallelogram, or a rhombus, which is a parallelogram, when they're on a slant, look at it, this diagonal here is definitely smaller than this diagonal here. So you would never set those diagonals equal. All right? Anything on a tilt is never gonna have equal diagonals. All right, but rectangles square up, so they wind up having equal diagonals. Okay, last one here. again involving the diagonals. If I told you DE, this small piece here, was 2x, and then I told you that the long piece, AC, was 5x minus 10, well, that's going to tie in two of the relationships you know. One, the diagonals of a rectangle are equal. Problem is DE isn't a full diagonal. But if you doubled it, if you doubled 2x, then you can set it equal to the other diagonal. So 2 times 2x equals 5x minus 10. And you can solve that. Or you could take the other route. If you know AC here is 5x minus 10, and remember in the other one we said, hey, this piece, this piece, this piece, and this piece are all four going to be equal, you could cut the bigger piece in half, so 1/2 of 5x minus 10, and set it equal to 2x. That's another way you can see that. All right, the trapezoids. All right, so here, if I gave you two base angles, and you remember the base angles are equal, set those pieces equal. Here I didn't give you base angles. I gave you, one obtuse and one acute. All right, so those two adjacent angles here, all right, are going to be supplementary. So 6x plus 4x plus 10 equals 180. Again, this is only for isosceles trapezoids. Same thing here with the diagonals, all right? That special property of isosceles trapezoids, same as it is with the rectangle, where the diagonals are equal. So if I did give you an algebraic expression for for AC, diagonal, and BD, diagonal, you would set them equal. That whole pieces thing that we just did with the doubling or cutting in half with the rectangle wouldn't apply here because the diagonals don't bisect each other on a trapezoid. Okay, 3 reminders. 1, if I was just to tell you you had rectangle MIKE but didn't give you a picture, you could put the M wherever you want. But just remember that MIKE has to go in order around the rectangle. So you'd have to either put I here, in which case then you have K and E, or you'd put I here, in which case K and E. But either way, the M and the K are going to be opposite angles. I and E would be opposite. K and E would be adjacent. Now, not a big deal with a rectangle where those angles are all the same, but if it was a parallelogram, M and K would be the 2 equal angles. I and E would be the 2 equal angles. All right, so be mindful of that. 2, so in this case, I tried to draw a parallelogram for you. So if all of a sudden I drew this extra line in here, that's not a diagonal. Diagonals connect opposite vertices. So, but if I could have a couple other applications in this. For instance, alternate interior angles. Watch my Z. Boom, boom, boom. All right, so this angle here and this angle here would be congruent. Those applications still apply because parallelograms, this side and this side are parallel, right? So you would get your Z, or in this case, your backwards dyslexic Z. All right. Also, I'd be forming a triangle right here. And you know that the 3 angles of a triangle always add up to 180. So all those pieces are always available to you. Don't forget about it. And a somewhat tougher application is, remember this. If I had a square and I only drew in one diagonal, it would work with 2, but it's easier to see with 1. If I only drew in one diagonal, squares are always going to be equilateral, right? So if you look at this triangle now, you got these 2 sides are the same, so that makes this triangle up top isosceles. But in a square, you know this is also a right angle. So that gives you an isosceles right triangle. So you could always use, all you need to know is one side, and you'd be able to use Pythagorean theorem, 5 squared plus 5 squared equals c squared, or x squared in this case, and you'd be able to solve for that diagonal length. All right, 5 squared, 25. 25 and 25 is 50. Square root of 50. But remember that simplifying that radical, rad 25 times rad 2, right, would simplify to 5 radical 2. Now, if you remember the lesson on 45, 45, 90 triangles, one of the 2 special right triangles we talked about, we said whenever you have an isosceles right triangle, it's always going to be a 45, 45, 90. 45, 45, 90. Whatever this side length is here, this side length will be here too. But this side, this diagonal, will always be that number times radical 2. So 5, 5, 5 radical 2. 10, 10, 10 radical 2. 13, 13, 13 radical 2. All right, so you always have that special relationship if you just forget about Pythagorean theorem, which you won't do anyhow. All right, so those are my explained applications. Hopefully that helps. Be careful in the CASEL learning assignment now. It's like 11 questions, I want to say, but you know, some of you have been rocking it and some of you have been struggling on it. If you watch these, it should really walk you right through everything, all right? Have a great day. Jump Trons for life.